back to section 14. In this video, we're going to be going over example 3. So example 3 is going to ask us to determine the source-free response of a circuit described by a differential equation. Now don't be freaked out by the words differential equation. You literally wrote and solved one in example 2. So if you remember, let me pull it back up here. There we go. We have our differential equation here. We even started. So d dt vx, 1/16 vx equal to 0. So that's all differential equation is. It's just a derivative. So this is a first order differential equation because we have a first derivative. And it's linear because none of our terms are squared. So it's a very common type of differential equation. And we're just going to learn patterns for solving these. Alright, so in order to do this, the technique we're going to use, so this is the S method. This is the one I prefer that you guys use. In the next example, we're going to learn a different method that you might use in other classes. So you can read this at your own speed, and basically we're going to follow these steps to find our response to that circuit. And before we do that, we need to kind of fill in these equations. So the complete response of a circuit, so let's write that down. So our complete response is x of t, because these are all be functions of t, equal to x particular plus x natural. So that's your first equation. So that x particular is going to be equal to 0 for right now. So that is because our right-hand side is 0. So as long as our right-hand side is 0, x particular is 0. And x natural, so this is the natural response. So this is kind of like the spring, is how long does it take for it to settle back down? Think a tuning fork. So last time we derived this equation, the form of it at least, and if you remember, it is a e to the s1t, where a is our constant and s1 is our root. So if we kind of look at this problem, we're going to rewrite this. So this is just kind of an equation in general. We use this a whole bunch. So we're going to rewrite this in terms of v of t. So v of t is going to be v particular plus v natural. And we know that our particular response is 0 because our right-hand side is 0. And we know that our natural response is going to take the form of a e to the s1t because it is a first-order linear differential equation. Basically, all your circuits that have a single capacitor or a single inductor will be first-order linear. So, a e to the s1t. So we'll just rewrite that. So v to the t, so v of t, sorry, a e the s1t. So you're going to see this a bunch for this section in your homework. And so we know when we solve this, we're going to get this form. And so our goals when solving this are to find a and to find s1. And this is going to be for t greater than 0. If you go back and look at the problem, it should tell you that it was at t equals 0. So let's scroll back down here. Yeah, so for t greater than 0. All right. So the first thing we want to do is we need to figure out how to find S1. So that's what we want to find first. You always find your constant A last. So find this last. So in our previous one, we solved for this. It was like -1/16. So we can find this if we have our differential equation. So what we do, we're gonna bring this back down. We're gonna write this as dt So there's a bit of a trick here. Sorry. So if you look through the notes, it'll show you this. So if we take the derivative of e to the s1t, we will get s1e to the s1t. And so if I take this and this is common on both sides, I can divide by the s1t, and I am left with d dt is equal to s1. So what we do is we bring that equation back down. So what I was trying to do is you bring this back down, and instead of writing d dtv, we're going to write s1v plus 6v equal to 0. So we do a substitution, is really what we should call this. And then we are going to divide by v. So when I divide by v, this one goes away and this one goes away, and I get 0 divided by v, which is 0. So then I get s1 plus 6 is equal to 0, which means that s1, our root, is equal to negative 6. So s1 equals negative 6. So if we hop back into our notes real quick, this means that our circuit is stable. So stability, we can look, if we look at the value of s1, so if it's negative, it'll be stable. If it's positive, it'll be unstable, and if it's 0, it'll be what's called marginally stable. So a stable system will decay back down and come back to rest. A marginally stable system is on that that edge. It could go stable or it could go unstable. These are generally theoretical systems. You can't actually build them in real life. An unstable system is one if you give it you've probably seen like the video of the bridge where there's a wind and then like the harmonic resonance just builds up and eventually the bridge collapses itself. That's what that looks like. So in general, you're not going to see that in these circuits unless you put some kind of a dependent source in there. Then you have a chance of being unstable. If it's just resistors, capacitors, and inductors, it's very unlikely to be unstable. So we found that S1 was negative 6, which means that it is stable. Alright, so let's rewrite our equation now. So if you remember, we have this thing here. We switch colors. So this was our equation. We knew it was going to be in this form, so we'll move it over here. V of t equal to a e to the s1. We now know s1. s1 is negative 6, so we're going to put negative 6t. And then for t greater than 0. So I'm not going to write that, but we'll add it back in here in a second. So now the goal is to find a. It's the only thing left that we don't know. So how do we find a? So what they have to do is they have to give you what's called an initial condition. So if you look back in the problem, they gave us an initial condition. They told us that V of 0 plus was 12 volts. So what does that mean? Well, that means the voltage right after we switch it off. So that's what it means by plus. So like if we draw the voltage, so like if I had kind of a chart here, and if we had, let's do that. So say this is V and this is T. So we have the voltage, it's up here at 12 volts. And then right here, just after it is 12 volts. And then I don't know what it's going to do next. I don't, so it should decay at some rate because it's discharging. But because it's a stable system, it should decay. So we know its starting point is what this means. So V of 0 plus is 12. So we know that it starts at 12. So we can take our equation up here, bring it down here, and set t equal to 0. So V of 0 is equal to a e to the negative 6 times 0. So e to the 0 is not 0, 1. So we get that V of 0 is equal to a, and we know that it's also equal to 12. So therefore a is equal to 12. And at this point, we're done. We just write V of t equal to 12e to the negative 6t for t greater than 0. All right, good job. In the next video, we will look at doing the same thing, but with a different technique.